This is Physics 1020 and 1090. The lectures for Wednesday, April 15th, were in Chapter 30 about nuclear energy. In this video 2, we're going to talk about the Chernobyl nuclear disaster. Well, last year here at Oakland University, there was an event that was about the Chernobyl disaster, which happened in 1986 in what's now Ukraine, but at the time was part of the Soviet Union. Now, the disaster at the Chernobyl was by far the worst nuclear reactor accident in history, by far. Many people died. It spread radioactivity all over. It became an international incident. Well, my job at that event was to describe why the physics behind the reactor design and why the reactor occurred. Now, it turned out I couldn't give the talk at the event, but I wanted to share this talk with you. So today, to kind of culminate our study of nuclear energy, I want to talk about the Chernobyl nuclear disaster. Okay, the nuclear reactor in Chernobyl had an inherently unstable design that led to the worst nuclear accident in history. To understand why the nuclear design was so unstable, we need to talk about some physics. Well, the nucleus of an atom contains protons and neutrons, and the number of protons determines what element you have. So for instance, if you have 92 protons, you have the element of uranium. The number of neutrons determines what isotope you have. So if you have 146 neutrons, then you have uranium-238. That is 92 protons plus 146 neutrons is equal to 238. Okay, uranium-238 is the most common isotope of uranium. Has about 99% of the uranium is uranium-238. Now, if your uranium nucleus has 3 fewer neutrons, so it only has 143 instead of 146 neutrons, then you have uranium-235. And uranium-235 is a rare isotope of uranium. About 1% of our natural uranium is uranium-235. Now, no stable isotopes of uranium exist. But both uranium-235 and uranium-238 have very long half-lives, nearly as old as the age of the Earth itself. So some of the uranium that formed with the Earth is still in our rocks today, and we can use them as the fuel for our nuclear reactors. Okay, although uranium-235 is the rarer of the two isotopes, it's the isotope that's responsible for nuclear fission in nuclear reactors. So uranium-235 is what's called fissile. That is, it's so close to being unstable that a single neutron can come in and cause it to break into two pieces. And when it breaks into two pieces, it releases energy, and it also releases 3 additional neutrons. This is called nuclear fission. Okay, so a nuclear chain reaction can start because you have a lot of 235, and you have a neutron comes in, and it breaks the uranium-235 into 2 pieces, releases 3 neutrons. Those 3 neutrons can go out and hit 3 other uranium-235 nuclei. And each one will break in 2 and then release 3 more neutrons. So now you have 3 times 3 are 9 neutrons. And each one of those 9 neutrons can go hit a uranium-235 nucleus. And it'll split them in 2. And now you have 9 times 3 are 27 neutrons. 27, the next generation, you have 81. The next generation goes on, and very quickly you have a massive release of neutrons. And with each one of those uranium fissions, you're releasing energy, so you have a massive release of energy. Now, fortunately, there are ways to control this release of energy so we can use it for peaceful purposes. But the atomic bomb that was dropped on Hiroshima at the end of World War II was based on uranium-235 uncontrolled nuclear chain reaction. Okay, now one surprising feature about uranium-235 is that slow neutrons work better than fast neutrons at causing fission. So how this was discovered is an interesting story. There was an Italian physicist, Enrico Fermi, who was trying to bombard a lot of various elements with neutrons to study what would happen. And he found that he could get more events, more fission, or more nuclear reactions occurring when he had his apparatus on a wooden tabletop than if it was on a marble tabletop. So what in the world Fermi must have been terribly confused. It turns out that the wood was better at slowing the neutrons down than the marble, and therefore made the experiments work better. In fact, Fermi got so confused that he got desperate. He went out to a pond in the back of the physics building and actually submerged the apparatus into the pond, and he found he even got more neutrons. So apparently something's acting to slow the neutrons down. Now, if uranium-235 works better at fission with slow neutrons, then if you want to use it in a reactor, you have to have some substance that's a moderator. That is, a substance that will slow the neutrons down. Now, the key to understanding the Chernobyl nuclear reaction is to understand the moderator. If we understand about the moderator, we can understand about the Chernobyl disaster. Okay, so the best moderators are materials that have a nuclear mass that's about the same as the neutron. So let's take an example. For instance, suppose you had a nucleus that was much heavier than the neutron. So here's your neutron. Here's some giant nucleus, say uranium. The neutron's going to come in, bang, and just bounce off. It's just going to bounce off. It's going to change its direction, but its speed's not going to change. It's not going to slow down. It's like bouncing off a brick wall. Let's look at another example. Suppose you have your neutron, and now it has a very light particle, like an electron. The neutron is going to come in here and just going to push that electron away, and it's going to keep moving. It's not going to slow the neutron down. It's going to speed the electron up, but the neutron is just going to keep going. It's like a big train smashing into a mosquito. It doesn't slow the train down. The neutron doesn't slow down. But suppose you had a neutron that hit some other particle that was similar in mass to the neutron. What you're going to have is, here's your neutron. Here's another particle. It's going to come in, bang, stop, and the other one's going to fly off. This is like billiard balls. You've all seen it when you're playing pool. You have your ball comes in, hits this ball stops, and this ball takes off and flies away. So if your two particles are about the same mass, they're going to be more effective at slowing the neutrons down. Now, what has a similar mass to the neutron? A proton. Where do you get a lot of protons? In hydrogen. So hydrogen is an excellent moderator. And where do you get a lot of hydrogen? Water. Water has H2O. Water has a lot of hydrogen. So water is an excellent moderator. In fact, it's the water that's inside the wood of the wooden tabletop that slowed Fermi's nuclei down and allowed the experiments to work better on a wooden tabletop than on the marble, where there is no hydrogen. And it's why when he went back out into the pond, he even got bigger results. There was more hydrogen around to slow the neutrons. So there's other elements that can also act as moderators. Any kind of light element's pretty good. For instance, carbon. Carbon has 6 protons and 6 neutrons. It's not real light, but it's lighter than a lot of elements. And it's a pretty good moderator. It's a little heavier than what you'd want, but it's got some advantages. It's abundant, it's cheap, and it's dense. So carbon in the form of graphite is another good moderator. So during the Manhattan Project, Fermi, remember Fermi, who is the Italian physicist, he had fled fascist Italy, came to the United States. So Fermi built the first nuclear reactor in a squash court under a football field in Chicago. And what he had is he had uranium mixed together with graphite. That's like the lead, or that's like the carbon in the graphite of your pencil lead, okay? So that's what he used. He used graphite for his moderator. So he basically had balls of uranium surrounded by big blocks of graphite. And he was able to build the first functioning nuclear reactor as part of the Manhattan Project during World War II. Now, before we talk more about moderators, I want to try to wonder why Fermi's reactor didn't just explode and cause an atomic explosion and take out Chicago. Well, one reason is Fermi used a mix of uranium-235 and uranium-238. In fact, 99% of the uranium he used was uranium-238. It's the 235 that's fissile. So, to make matters worse, sometimes uranium-238 can absorb a neutron. So here's your uranium-238. Sometimes your neutron just comes in and sticks to it. And now you have uranium-239. This would basically take neutrons out of action. So it's worse than having just nothing. It actually absorbs neutrons, and that can slow the nuclear reaction. So that was one problem. And how also Fermi could control his nuclear reactor. He didn't want it to explode. So he used what's known as control rods made out of cadmium. Cadmium is a type of material that's very good at just absorbing and sucking out neutrons. So cadmium, he could use cadmium control rods to control the nuclear reactor so it wouldn't explode. So Fermi was careful and he was able to run this nuclear reactor. But it's kind of funny, the story about Fermi's reactor. He had this one big control rod. It was kind of the rod of last resort that was hung by a rope above the nuclear reactor. And if things got out of control, that control rod is supposed to drop down and put out the nuclear reactor and dampen the chain reaction. And so there's a fella up there who stood next to the control rod rope. His job is he had an axe, and if things started going out of hand, he was supposed to cut the rope, and down would come the control rod and dampen out the nuclear reaction. So it's kind of scary to thought that that was all that was between us and a major nuclear disaster. But as it turned out, Fermi was very careful, kept his nuclear reactor under good control, and he did not have any accidents. Probably it wouldn't have exploded like a bomb. Probably what would have happened if it just would have gotten very hot and then melted, and you'd have what's known as a meltdown. And the meltdown would have spewed radiation all over Chicago, and it kind of been an accident very similar to what happened at Chernobyl. But we were in a war, so they took some chances. They built this reactor and to try to see if they could control nuclear reactions. Okay, back to the nuclear moderators. Okay, let's consider 3 different types of moderators. First, I want to talk about heavy water. Okay, heavy water is when you take the rare heavy isotope of hydrogen. Normal hydrogen is hydrogen 1, just a single proton, but sometimes you get a hydrogen as hydrogen 2. It has a proton and a neutron. Okay, so this is actually a very good moderator. It's not quite as good as hydrogen 1, but it's a very good moderator. It has an advantage. Sometimes hydrogen 1 can have a neutron come in and it'll stick to it and create hydrogen 2. And that's like the cadmium rods. It sucks the neutrons out of the system, out of the chain reaction, and dampens the reactor. So if you want to just slow the neutrons but to not dampen the reaction, you want to increase the reaction by the moderator, hydrogen 2 has certain advantages. It may not be quite as good a moderator at slowing the neutrons down, but it doesn't stop the neutrons, suck the neutrons out of the system. So you take this hydrogen 2 and you use it to make water, H2O. Instead of 2 atoms of hydrogen on the oxygen, you have 2 atoms of deuterium, the heavy hydrogen on the atom. You have heavy water. Heavy water is a great moderator for nuclear reactors. In fact, during World War II, the Germans were also trying to build atomic bomb. And they wanted to create an atomic reactor just like Fermi was trying to build one. And they were going to use their as a moderator. Instead of graphite, they were going to use heavy water. And they knew that heavy water would be very effective as a moderator. In fact, heavy water is very expensive to produce. There was a plant in Norway that produced heavy water, and the Germans controlled Norway. So the English got word of this, and they sent a group of a squad up to Norway, and they basically sabotaged the plant and blew it up, and all that precious heavy water just drained down the drain. Okay, so nowadays heavy water is so expensive that they don't usually use it in nuclear reactors. So we're not going to discuss heavy water anymore. Second moderator I want to talk about is just regular old water using hydrogen 1. I'll call that water as opposed to heavy water. Okay, nowadays, most nuclear reactors in the United States use water as the moderator. Now, water has 2 purposes. It's the moderator, and it's also the coolant. Why do you need a coolant? Well, you need the coolant to keep the reactor from getting too hot and melting down. And you also need the coolant in order to get the energy out. Basically, the water gets hot and then is extracted and used to drive a steam engine to produce electricity. So the water in the United States, water has 2 purposes. It's going to be used as the moderator and the coolant. Now, suppose you have a reactor and for some reason, not sure what, but for some reason it starts getting too hot. If it starts getting too hot, the water will boil. As the water boils, it goes out of the system, water goes away, and there's no more moderator slowing down the nuclear reaction. No more moderator, the neutrons don't slow down, they're not effective at producing fission, and you have less nuclear reaction. So, it gets hot, and it turns off the reaction, and then it'll begin to cool down again. So this is sort of a type of a negative feedback loop. It's like the negative feedback loop controlling the temperature of your house. The furnace is on. If it gets too hot, the thermostat turns the furnace off and you cool back down. Negative feedback prevents a runaway reaction in nuclear reactors where water is the moderator. So, now you might remember that sometimes hydrogen 1 will absorb a neutron and that'll take it out of action. So in some ways, hydrogen 1 kind of acts the opposite of the moderator. It makes the reaction increase, but the moderator affects the main effect. So as you have the moderator leaves by boiling away, the reaction slows down, turns off. We say that the reactors of this type have a negative void coefficient. Now, void refers to water bubbling and boiling, forming bubbles. Negative means you have a negative feedback loop occurs that keeps the reactor from going out of control. Now, for a third type of moderator, I want to consider is carbon, just like Fermi used. The Russians have built something called the RBMK reactor. Now, that's a Russian acronym, so I'm not going to try to explain what the different letters mean. But basically, RBMK reactor is a reactor that uses carbon as the moderator. It uses water as the coolant. So the water is still in the reactor as the coolant, but the main moderator is carbon. So Chernobyl was an RBMK reactor. Now, just like in Fermi's original reactor, the graphite's the moderator. And let's imagine what happens when this reactor starts getting hot. It gets hot, the water boils off, but the water is not the moderator. So the reaction doesn't die out. The reaction continues. And in fact, the water was sometimes, those hydrogen were absorbing neutrons, taking them out of action. That's not going to happen anymore. So, and actually, when the water boils off, the reaction goes even faster. So the water boils off, the reaction happens even faster, produces more heat, produces more water boiling off, which makes the reactor go even faster still, which produces more heat, and what you have is positive feedback. You have a vicious cycle. And that can cause a explosion. Okay, so this reactor has what's called a positive void coefficient, meaning that it's as if your thermostat in your house was wired wrong. So as the furnace ran and made the house too hot, the furnace, instead of turning the furnace off, the thermostat makes the furnace even stronger, even work harder, and its house would get even hotter, which would make the thermostat make it even work harder still, then turn the furnace up even still, and you get this positive feedback loop. So if you have this kind of thing happen, you will get a dramatic and quick rise in the heat, and that's exactly what happened at Chernobyl. Okay, now, why do we have nuclear reactors? Nuclear reactors we have them so we can produce steam from the water that can then drive a steam engine and make electricity. That's why we have these reactors. So once you get the steam driving a turbine, it's got to be under high pressure. So these nuclear reactors usually have water under high pressure. All right. Now, if the pressure builds up, if it gets too hot, the pressure is going to build up until eventually it's like a pressure cooker. It can no longer withstand the pressure and it explodes. And it breaks open and it will release all this steam. And all the steam won't be just steam. It'll all be steam mixed in with all sorts of radioactive elements. So what it's going to do is spew hot steam, radioactive steam all over the place. It's kind of like your whistling teapot. When it begins to boil, it sprays steam, but instead of doing it just it's going to go boom and spread a big clouds of radioactive steam all over the place. There's another problem with these RBMK reactors is that the moderator is carbon, and carbon burns. So once the reactor breaks open, oxygen come in, and basically carbon is like coal. It will begin to burn, and it'll burn and spew smoke, radioactive smoke all over the place. So in fact, Many of the people who were killed at the Chernobyl nuclear accident were killed because were firemen who were trying to put out the fire and then exposed to all this radioactivity when they were trying to dampen the fire at the Chernobyl site. Okay, there's another issue that's a little less important, but it's still something I want to bring up, and that's the control rods. Now, Chernobyl had control rods that were made out of boron, which are kind of like cadmium, and they suck up the neutrons. Problem was, they had these control rods, all the boron, but the tips, like the cap of this pen, the tips of the control rods were made out of carbon. So when you first stick in the control rod, the first thing that happens is the carbon acts as a additional moderator, and that speeds the reaction up. And it was only once you get the control rod completely in that you can actually have it suppress the reaction by absorbing the neutrons. So the control rods work great as long as things happen rather slowly. But if there's a sudden rapid increase and you try to respond by putting in the control rod, the very first thing that would happen is that you would actually make matters worse. So at Chernobyl, the problem, when it did developed very quickly, and the control rods couldn't keep up. So I'm not going to go into all the comedy of errors that were the immediate cause of the accident at Chernobyl. They were doing some kind of tests, and the tests required them to turn off some control features that they had. And some of these safeguards were still in place, but they had a lot of mistakes. They had poor communication and ignorance, and prevented them from all these safety features from working. So what happened is the reactor got out of control and then very quickly exploded and spewed radioactivity all over the place, and that was what caused the Chernobyl disaster. Now, you could say that the direct cause of the Chernobyl accident was all these problems that caused the Chernobyl reactor to get out of control. But really, inherently, the main underlying cause was the bad design, the unstable design of the Chernobyl nuclear reactor. It was really a disaster waiting to happen. So it's not surprising that these types of RBMK Russian nuclear reactors were really an accident waiting to happen, and eventually it was almost certain that one of them would cause a major nuclear disaster.